of the actual calculation of multiple regression using SPSS, I want to take some time going through the material in Chapter 2 that shows us a number of different tables and what they look like as published findings. So we have, we'll talk about the SPSS output and how to interpret that next week as we move forward. But when you read journal articles, you'll often find tables and multiple regression equations published in the results section. And so Chapter 2 in Allison's book really goes through how those tables might be set up, some of the most common ways that they are set up, and then how to interpret what is in those tables and what that tells us about the variables being studied. Table 2.1 in Allison's book provides us with an example and an opportunity to practice the interpretation of regression output. This isn't what SPSS output looks like. We'll look at that again, as I said, later. But let's take a few minutes to go through each component of this table. For each variable, there is a b and a beta value. Recall that these values are our slope. They are our unstandardized and standardized regression coefficients, our slope coefficients. They tell us how much change occurs in the dependent variable for a unit change in the independent variable. So here we can say that self-reported health goes up 0.076 for each year increase in education. So that's how we interpret those slope coefficients. Note the inclusion of both standardized and unstandardized coefficients. Recall that standardized coefficients allow for easy comparison across variables that have different size units. And these are standardized standard deviation units. And they allow us to make comparisons between variables more easily. For example, even though age in years has a smaller unstandardized coefficient compared to marital status, so 0.013 compared to 0.105. The beta coefficient, or standardized coefficient, shows us that it has a great deal more impact on the dependent variable than marital status. So if you compare the beta coefficients, you see 0.247 and 0.058. The large number of response categories in age and years make the unit change seem less impactful when you're looking at just the unstandardized coefficients. So it's important to look at both of those. The greater statistical significance of age gives us some clue about the larger impact that it has compared to marital status, but the beta coefficient does a better job of illustrating this to us immediately. The asterisks after some of the slope coefficients in equation 1 and 2 indicate and identify statistically significant relationships or impacts of that independent variable on the dependent variable. On the right, you have the beta coefficient or standardized coefficient. There's no need to put statistical significance markers on both of those because the beta is just a standardized unit. It doesn't make any other change to it. Note as well that statistical significance is not the same thing as large effect. A variable can be statistically significant in terms of its impact, but that impact could be very small in unit terms. So again, we compared age 0.013 and marital status 0.105. And if you compare those, they're both statistically significant, but the impact is a lot smaller. And even 0.013 for race, we have 0.239, which seems pretty large until we can compare it to our beta coefficient. And then it has a much smaller impact than some of the other variables, such as education. The value in parentheses under our slope coefficient is the standard error for that independent variable. Notice that there are two equations. Equation 1 provides us a set of demographic variables and their impact on the dependent variable. So the first equation provides for a set of demographic variables. So we have sex, race, age, education, marital status, and so on. The second equation adds in some additional variables such as employment, income, economic hardship, work fulfillment. At the bottom, you can see that when we add these second set of variables, the values in our socio-demographic variables change. Education goes from 0.076 to 0.041, for example, and sex goes from 0.114 and being statistically significant to 0.051 and no longer significant. So the use of multiple equations and the reporting of multiple equations is done to illustrate how much better the model explains when additional variables are added into the equation. So we can see that the model is a better fit now with the additional controls added. It also illustrates how some of our initial variables and their impact changes when these additional controls are included. So equation 1 is just looking at demographic variables alone. Equation 2 adds in a number of other variables that we think may have an influence, and we can see that it can sometimes change what's going on in terms of those demographic variables. So adding those other things in, and we'll talk about why that might happen later when we talk about some of the issues that we face with regression in chapter 3. At the bottom, there is listed a constant value and an R-squared value. The dependent variable is self-reported health, and everything in the table helps us to understand the factors that influence someone's self-reported health score and how influential each variable is on that health score outcome. So in the table, constant is used for the term intercept. So the constant value is the intercepts in these two equations. And again, it doesn't really tell us that much, but it's our estimate of how someone with a value of 0 on all the independent variables, it's what their health reported score would be, right? So that's what the constant is, the intercept is. So when all variables are 0, when all independent variables are 0, this is the value of y, right? And again, it doesn't give us, it's not terribly interpretable, but it only exists there to tell you where it crosses the y-axis. The R-squared value tells us how well we can predict the dependent variable, knowing only the independent variables in the model. And we can see that the difference between the first equation and the second equation tells us that we have improved our ability to predict health score by including the employment variables in the second equation. We go from 15% explained variance to 23% explained variance. And 23% isn't really that big. So clearly there are a lot of other factors that aren't being accounted for in our models. But Allison points out that we shouldn't really worry too much about small R-squared values as long as other parts of our model are functioning and that we find that these things are statistically significant. So what would our equations look like? For equation 1, it might look like this. So you can see that it gets pretty complicated. So we have in our equation, this is our intercept for equation 1, 3.413. So y is equal to, remember, y is equal to a plus bx. So we have a, our intercept value. And then for each of our independent variables, education, sex, race, and marital status, and this is for equation 1, we are going to take our slopes and plug those in. And I believe I made a mistake on this. Something didn't get carried over quite right. Oh, I skipped age somehow. Okay, which explains why there's no negative value in there. So we're going to plug these into our equation. I apologize that I left out age, but that's where all of these go. And you should also have a minus 0.013, x. That would be for age. And so that's what that regression equation would look like. The second equation would have even more factors because it would have markers for each one of these. So we would plug in our intercept, 3.729, and then each of our independent variables with its slope coefficient. But I just want you to see how that plays out in terms of what the final equation ends up looking like with these outcomes. Allison knows that when interpreting some of these coefficients, we have to be careful because some of the units, some of these variables are not interval ratio, and units don't mean numerical values in the same way for ordinal level variables as they do for interval ratio level variables. Note as well that statistical significance is not the same thing as large effect. We talked about this already. Note also the use of dummy variables that are coded as 0 and 1, and what this does to the interpretation of the equation when we're talking about the unit change from 0 to 1 in a dummy variable. So sex is measured as a dummy variable. Male is equal to 1, female is equal to 0. So we would interpret this not as a unit change, but as males versus females. So we could report, quote, males have self-rated health averages 0.114 units higher than females. So how would we report the employment dummy variable here? So if we wanted to report employed full-time, note the little notation at the bottom. So this is compared to not employed for reasons other than health. So how would we interpret the employment dummy variable for employed for full-time? Each of these dummy variables for employment, and there are several of them. So we have employed full-time, part-time, and unable to work. All of these are compared to not employed for reasons other than health. When you create dummy variables, you always leave one of them out. You include all of the others, and then that one is called our reference category. It's the one each one of them is compared against. So when making our interpretation with regard to the regression equation, we have to make it in reference to that reference category that is excluded from that analysis. So we can say, for instance, that those employed full-time reported health averages or self-reported health scores 0.174 units higher or points higher than those not employed for reasons other than health. So 0.174 units higher than those not employed for reasons other than health. Here we would say individuals who worked part-time had self-reported health scores 0.109 units higher than those not employed for reasons other than health. Now what happens here? Those who are unable to work, this is a pretty powerful measure. Those who are unable to work reported health scores 0.835 units lower than those who were not employed for reasons other than health. Now this makes sense. If somebody's unable to work, but it's not for reasons, it's not for health reasons, this unable to work is probably the health-related reasons, because not employed for reasons other than health and then unable to work. So we would expect that they would have health scores lower because they're probably ill, and that's probably the reason that they can't work.